Welcome back to Concrete 101. Last time, in part 1, we talked about aggregates, a very important raw material in our concrete. We discussed the properties of aggregates such as size, shape, and texture. We also talked about the sources of aggregates, including natural aggregates and manufactured or crushed aggregates, and how the sources affect the aggregate properties. We talked about two specialty aggregates, including lightweight aggregate used to make lightweight block, and the use of regrind or recycled concrete as an aggregate. Today, we'll talk about how we decide which aggregates to use and how much of each aggregate to put in our mix. We'll discuss particle packing, gradations, and aggregate blend curves. So let's get started. Particle packing sounds like something from a Star Wars transponder, but it's actually a fundamental fact of life for all concrete producers. It's so basic, it's easy to overlook when things are going well, but it impacts almost everything that we do. All concrete is made up of aggregate particles, glued together by water and cement paste. Units with larger spaces or voids between the particles need more cement to fill in the gaps, or the unit may have lower strength, lower density, and higher absorption. Here's an example of a poorly graded aggregate with only one size of particles. Notice the space between the aggregate particles. This unit will need a lot of cement paste to fill in those voids. A well-graded or continuous grading has a good balance of particle sizes from largest to smallest. This unit will need a lot less cement paste. In many cases, blending two or more aggregates together is a good way to achieve an optimum grading. Another common problem is flat, elongated particles. These cause two big problems: bridging, where long, flat aggregates block the movement of cement paste and other aggregates, and breakage, because the thin, flat shape is inherently weak and vulnerable to be easily broken, which can lead to low compressive strengths. So what do we mean by gradation? Technically, aggregate gradation refers to the distribution of range of particle sizes. How do we figure out the particle size distribution? As you can see, that's hard to quantify by eye. We need some equipment and a standardized test to help us out. Luckily, ASTM C136 tells us how to do a sieve analysis. To do a sieve analysis, we start with a nest of different sieve sizes, with the largest opening size at the top and decreasing to the smallest opening with a pan at the bottom. Take a representative aggregate sample and feed it into the top sieve. Mechanically vibrate the sieves in a set manner and time. Then weigh each sieve and calculate the percent that is retained. Then we plot out how much is retained on each individual sieve, and the result is a graph or grading curve, with the coarser large sizes on the left and the finer small sizes on the right. This is a typical curve for a 3/8" stone. We also use the gradation results to calculate fineness modulus, or FM, which is a number that represents the average particle size.
So before we start this section, here's a question for all you math whizzes out there. What's the connection between a dead bird and an Excel spreadsheet? While you think about that, let's move on. We also use the gradation results to calculate fineness modulus, or FM, which is an index number that represents the average size of particles. It's an indicator of the coarseness or fineness of a single aggregate or aggregate blend. The higher the FM, the coarser the aggregate. The lower the FM, the finer the aggregate. FM is calculated by adding the cumulative percentages for the mass retained on the sieves and dividing by 100. The FM of our 3/8" stone is 4.93. Also shown on the graph is the curve of a typical sand. It has a lower FM of 2.52, and you can see it's much finer than the 3/8" stone. So you may ask, This seems like a lot of work for a bunch of rocks. Why should I care? Well, because the consistency of our aggregate sizes is very important to our final product quality. A little work up front can save you a bunch of trouble down the line. Significant changes in aggregate supply can show up as batch-to-batch inconsistency in the texture of our final concrete product and cause other problems in production. Many times, the FM calculation will alert you to aggregate changes so that any issues can be proactively addressed. It's very important to know what your aggregate gradings and FMs are and to keep records of them. For those of you pondering that dead bird, the clue is that it's a canary, the bird that alerted coal miners to danger ahead. Changes in our FM calculations can be an early warning sign to alert us to trouble ahead for production. Now that we have the grading curves for our individual aggregates, how do we decide how much of each aggregate to use in our concrete mix design to ensure optimal particle packing? First, to understand the importance of particle packing, let's talk to Klaus in the lab.
Hi there, folks. This is Dr. Klaus von Baldguy, and we're here to talk about the word of the day, which is gradation. So here we've got a large, or what we would refer to as coarse aggregate. This is crushed or manufactured stone. Some of this might be a little bit larger than you would use, but in some big products we use those. This is a medium-sized crushed or manufactured aggregate. Typically you'd use that in most all of your products. And then we also have a sand here, or a fine aggregate, that we part of the blend to make all of your products as dense as possible and as low in absorption as possible. So now what we're going to do is take all of these aggregates we just talked about. We're going to put them in our blending jar here, which would be a little bit like your mixer, not exactly like your mixer. And then we're going to show you how these aggregates fit together and try to make a dense product. Start with a large aggregate. And now you look and see what we try to get is all the aggregates to fill in all the voids to make this as dense as possible and lower the absorption of your concrete. And that, my friends, is your word of the day from Dr. Klaus von Baldguy. Good day.
Okay, stick with me now. We're almost there. There is one more step. Just like we saw with Dr. Klaus and his mix, we need to figure out the best combination or blend of coarse and fine aggregates to optimize the particle packing. Over time, the industry has developed ideal grading curves for block, pavers, SRW, and other kinds of units. So the really hard part has been done for us, and we don't need to reinvent the wheel here. We can compare these ideal industry curves to the grading curves for our particular blend of aggregates. How our aggregates fit or don't fit into the ideal curve lets us predict how our aggregate blend is going to perform. Sometimes the curve will show a gap or deficiency in certain sieve sizes. In other cases, we may have an excess in some sieve sizes. In older times, we used to blend aggregates to hit an overall FM for the aggregate blend. While this gave us an idea of the overall average coarseness of the blend, FM only tells us about the average size of the aggregates and not about the actual shape of the blend curve, and shape matters. Let's look at an example from paver production for a utility paver with an FM of 3.40. An optimum grading curve for pavers is an M curve with peaks on the number 8 and number 50 sieves. The coarse peak on the number 8 sieve helps break up the concrete in the mixer and helps drive it into the mold, while the fine peak on the number 50 sieve helps fill in around the coarser aggregates to give us a paver with a high density and low absorption. This is an example of an aggregate blend that has an FM of 3.40, but which does not fit the optimum grading curve at all. It will not make a good paver. If we select different aggregates, we can blend them to have the right FM and a better fit to the optimum curve to give us a better performing paver. So let's review what we've learned about aggregates. Aggregates are a very important part of our concrete because they're the largest component of our mixes. It influences both the appearance and overall performance of our concrete products. We use a combination of coarser aggregates and finer sands. Poor performing aggregates lead to production problems and follow-on problems like low strength and poor quality. Size, shape, and texture matter, and when deciding which aggregates to use, we determine the particle size distribution or grading of each aggregate by doing a sieve analysis on each one. Then we blend 2 or more aggregates together to get good particle packing, which means that all the aggregates fit well together. To get an optimized blend, we choose just the right amount of each aggregate so the overall blend fits our target curve. For pavers, the target curve is a M curve with a coarser peak that helps drive the mix in a mold and a finer peak for filling in around the coarser particles. This maximizes our concrete density and gives us improved performance at the lowest cost. That's it for today. See you next time.
So that's all for today, folks, but feel free to check back with us anytime on our website, acmchem.com, where you can get more information and more videos on Concrete 101.